Massive stones were moved without wheels and fitted without gaps, yet this is not a fantasy. It is our shared human history. We are about to explore 30 ancient engineering feats that modern machinery still struggles to replicate. By the end, you will see human history not as a slow climb, but as a story of forgotten peaks of brilliance. How did cultures with simple tools achieve precision that challenges our best machines, and why were some of their methods lost for centuries? What do you believe is the true limit of ancient ingenuity? These achievements separate themselves not by their age, but by the profound gap between the tools available and the results achieved. Ancient engineering mastery is defined by a unique convergence of constraints and brilliance. The builders did not have computer models, electric power, or mass-produced steel. What they possessed was something arguably more powerful, a deep, patient, and intuitive dialogue with the natural world. They were not just constructing objects, they were collaborating with physics itself. This required a level of empirical observation we can scarcely appreciate today. Think of an architect who did not just study the sun, but lived by its rhythms for decades, learning exactly where its light would fall on the winter solstice to within a fraction of an inch. Their blueprints were not on paper, but in tradition, in song, and in the accumulated knowledge of generations passed down through practice. Experts like Dr. John describe these individuals as the ultimate pragmatists. They solved monumental problems not with theoretical abstractions, but with the materials directly at hand, manipulating stone, wood, and earth in ways that maximized their inherent strengths. This pragmatism led to a core principle of ancient engineering, building for eternity. While much of our modern infrastructure is designed within decades, requiring constant repair and replacement, these ancient feats were intended to outlast civilizations. And they have. This forces a humbling question. What fundamental principles of load distribution, of material science, of environmental integration did they grasp so intuitively that we, with all our computational power, sometimes fail to replicate? It suggests a knowledge not just of how to build, but of how to let the structure simply exist in harmony with the forces around it, enduring not by fighting nature, but by becoming a part of it. This foundational mystery, the art of achieving more with less in a way that stands the test of, is the lens through which we must view each astonishing feat to come. That principle of eternal harmony finds its ultimate expression in the desert sands of Egypt. The Great Pyramid of Giza stands not merely as a tomb, but as a silent argument against our assumptions about the past. For a structure built around 4,560 years ago, its precision is not a charming artifact of a simpler time, it is a mathematical rebuke. Consider the ground it rests upon. The pyramid's base, covering an area equivalent to about 10 city blocks, is virtually a perfect plane. Surveyors have found it is level to within just over half an inch from corner to corner. To put that in human terms, if you poured water across its entire foundation, the deepest puddle would be shallower than your thumb. This was accomplished on a site of naturally uneven bedrock, with nothing but copper tools, ropes, and an unimaginable depth of patience. Then, there is its orientation. The four sides are aligned almost perfectly to the four cardinal directions, north, south, east, and west, with an error margin of less than 1/15 of a single degree. This is not roughly north. This is a precision that rivals what we could achieve today with advanced equipment. How did they do it? One compelling theory involves the ancient Egyptians observing the circular motion of a single star around the celestial pole. By marking the points where the star rose and set on the horizon over a single night, they could bisect the angle to find true north with astonishing accuracy. It was a slow, meticulous dance with the night sky, translating cosmic motion into terrestrial geometry. The scale of the labor is almost beyond comprehension. An estimated 2.3 million limestone blocks, each weighing on average 2.5 tons, were floated down the Nile, dragged across the desert, and hoisted into place. The interior chambers are lined with monolithic slabs of granite from a quarry over 500 miles away, some weighing up to 80 tons. That is heavier than a modern tank. Modern engineers with diesel cranes and flatbed trucks would find moving just one of those stones a major logistical undertaking. The ancient builders moved dozens and placed them with gaps between stones often thinner than a credit card. This was not brute force. It was a symphony of organized labor, ingenious ramp systems, and a profound understanding of leverage and friction. Even with our technology, replicating the entire construction process within the estimated 20-year timeline remains a daunting, perhaps impossible challenge. The pyramid's secrets are not just in its mass, but in its mind. The precise angles of its internal shafts point directly to significant stars in the ancient sky, suggesting the structure was also a colossal stone telescope, a calendar, and a map of the heavens frozen in limestone. It embodies a terrifyingly advanced knowledge, not of machinery, but of the world itself. So we are left with a haunting question. If this is what they built when their goal was a permanent resting place, what other heights did their everyday engineering reach? Heights that have simply vanished back into the earth. The pyramids teach us that ancient builders thought in terms of geological time. But in the mountains of Lebanon, they appear to have thought in terms of geological weight. The Roman temple complex of Baalbek is a place of staggering scale, where the line between architecture and landscape blurs. Here, resting high upon a platform of smaller stones, are three behemoths known as the. Each is a single block of limestone, roughly 64 feet long, 14 feet high, and 13 feet wide, with an estimated weight of 800 tons. To visualize that, imagine three fully loaded jumbo jets, carved from solid rock, and then stacked with breathtaking precision to form a retaining wall. This alone defies logic, but the true heart of the mystery lies a half-mile away in the ancient quarry. There, partially cut from the bedrock, rests the stone of the pregnant woman, a monolith that makes the blocks look almost manageable. It measures over 69 feet long, with a weight scholars estimate at around 1,000 tons. That is over 2 million pounds of solid stone, still waiting for a journey that never began. The immediate question is obvious. How could any civilization, even the master engineers of Rome, move such a mass? Modern engineering is not helpless against these weights. The world's largest mobile cranes can lift well over 1,000 tons, but lifting in a controlled, prepared industrial setting is one thing. The challenge at Baalbek was one of terrain and precision. Moving an 800-ton block half a mile from the quarry, up a gentle incline, and then positioning it perfectly atop a wall many feet high, with margins of error measured in fractions of an inch, is a logistical nightmare even today. It would require a custom-built, massively reinforced transport system, an incredibly stable and wide roadbed, and a method of final placement that remains hotly debated. Some researchers propose a system of enormous wooden cradles and armies of men pulling on ropes, while others suggest ingenious levering techniques that turn the stone itself into a slow-rolling cylinder. The sheer manpower required, coordinated over months for a single block, speaks to an organization and a political will that is almost as impressive as the engineering. Yet, a deeper layer of mystery unsettles the narrative. The Romans certainly built the magnificent temples that crown the platform, but many archaeologists now suspect the colossal foundation, including the, is far older. The style of stone cutting and the mind-boggling scale do not perfectly match later Roman work at the site. This suggests the Romans may have found these Cyclopean walls already in place, the work of a lost, megalithic culture, and simply built their own temples atop what they could not explain. If true, it means the greatest stone-moving feat at Baalbek might not belong to the famous empire with its cranes and arches, but to nameless builders from a forgotten age, whose techniques for manipulating the earth's bones have vanished without a trace. The stone of the pregnant woman, then, is not just an unfinished block. It is a silent question, left in the quarry for, were the builders interrupted, or did they finally encounter a challenge even their legendary skill could not overcome? From colossal stones to a device that fits in a shoebox, the next leap in ancient engineering is one of breathtaking miniaturization. In the year 1900, sponge divers off the coast of a Greek island called discovered a shipwreck from the 2nd century before the Common Era. Among statues and pottery, they recovered a lump of corroded bronze and wood, so encrusted it seemed like worthless debris. Decades later, a researcher noticed a gear wheel embedded in the rock-like mass. This unassuming object, now known as the mechanism, would shatter our understanding of ancient technological capability. It has been called the world's first analog computer, and that is not an exaggeration. The device was a complex astronomical calculator, operated by a hand crank that turned a network of at least 30 interlocking bronze gears. These meshed with a precision that would not be seen again in Europe until the mechanical clocks of the 14th century, over 1,500 years later. Its purpose was to model the cosmos. By turning the crank, a user could predict the positions of the sun and moon, the phases of the moon, and even the timing of solar and lunar eclipses. It tracked the cycles of the 5 known planets and, remarkably, the 4-year cycle of the ancient Olympic Games. This was not a simple calendar. It was a dynamic, mechanical representation of the heavens, a portable planetarium built with gears and dials. Modern researchers, using tools like 3-dimensional X-ray tomography, have peered inside the corroded blocks to map its intricate gear trains. They discovered differential gearing, a technique thought to have been invented in the 16th century, which allowed the mechanism to account for the moon's irregular orbit. The craftsmanship is staggering. Each gear was hand-cut from a sheet of bronze using files and simple drills. Their teeth were shaped and spaced with such consistency that the entire assembly meshed and turned smoothly. To design this, the unknown creator needed a profound synthesis of knowledge. They required advanced astronomy to understand the celestial cycles, sophisticated mathematics to calculate the necessary gear ratios, and masterful mechanical engineering to translate those ratios into a physical, working model. While we can now create flawless replicas using computer-aided design and electric machining, the original feat stands alone. It represents a flash of theoretical and practical genius in the Hellenistic world that appears to have no precedent and left no immediate successor. The mechanism feels like an artifact out of time, a single, sophisticated peak that rises from the historical record and then vanishes. Its existence forces a humbling question. If this one device survived by the sheer chance of a shipwreck, how many other pinnacles of ancient precision engineering have been lost forever, leaving no trace for us to find that leap from intricate bronze gears to the monumental stones of the Andes reveals a different kind of genius, one rooted in an intimate conversation with the land itself. High among the clouds, the Inca stonemasons performed a kind of magic with rock. At sites like and the fortress of you do not just see walls, you witness a geological puzzle. Enormous blocks of hard granite and diorite, some weighing over 100 tons, are shaped into irregular, multifaceted forms. They fit together in complex, interlocking jigsaw patterns, and they do so without a single drop of mortar. The joints are so phenomenally tight that for centuries, observers have claimed not even a sliver of paper can slide between them. This is not an exaggeration. The perfection is visible, a seamless stone tapestry where one giant block flows into the next with a precision that feels impossible for human hands. This technique is called ashlar masonry, but for the Inca, it was far more than a construction method, it was a profound survival strategy. The Andes are one of the most seismically active mountain ranges on Earth. A rigid, mortared wall would crack and crumble under the relentless shaking. The Inca walls, however, were designed to dance. During an earthquake, these polygonal stones, with their subtle, rounded edges and intricate fits, can shift and sway against one another. The energy of the tremor is dissipated through a million tiny movements across the surface of the wall. Then, when the shaking stops, the stones simply settle back into their original, locked positions. It is a breathtaking example of engineering that works in harmony with natural forces, not against them. The mystery deepens when we ask how they did it with such basic tools. The prevailing theory is that they used harder stones as hammers to pound the granite into shape, slowly pecking away at the surface. They likely used sand and water as an abrasive to grind and polish the faces, a process requiring immense patience. But the real lost art is in the fitting. How did a mason, working on one colossal, irregular block, know exactly how to shape its neighbor? They could not simply measure and copy. Each block was unique. The leading hypothesis is a process of direct transfer. A mason would shape a prototype block, perhaps from a softer stone or clay. Then, using a paste of colored clay, or they would coat the finished face of this prototype. They would press it against the rough, wading granite block. The colored paste would transfer only to the high points that made contact. The mason would then painstakingly grind down those marked high points, repeating the process over and over, for days or weeks, until the entire surface area bore the colored imprint, signaling a perfect match. It was a tactile, iterative dialogue between two stones, mediated by human skill. Modern stonemasons with diamond-tipped saws and computer-guided mills can certainly achieve similar precision on a single block. But to replicate the entire Inca process, using only their presumed tools on hundreds of irregular stones for a single wall, becomes an exercise in almost unimaginable time and labor. It speaks to a culture that valued permanence and resilience over speed, where the work of generations was woven directly into the bones of the mountains. Their walls were not built on the land, they were grown from it, a testament to an engineering philosophy where the final, perfect seam was not just a technical achievement, but a form of reverence. While the Inca mastered stone, another ancient culture performed a different kind of alchemy, one that turned common iron into a timeless monument. In the heart of Delhi, a single iron pillar has stood in the open air for over 1,600 years. It is not its modest height of 23 feet that astonishes visitors, but its flawless surface. In a region with scorching heat, heavy monsoon rains, and pervasive humidity, this pillar of pure wrought iron shows no significant rust. It gleams with a dark, metallic luster as if it were forged a century ago, not during the Gupta Empire around the year 400 of the Common Era. This is not a story of a sheltered artifact, but of a material defiance that has lasted for 16 centuries of weathering. For modern metallurgists, the pillar is a profound puzzle. We can easily create stainless steel today, but that relies on adding chromium in controlled industrial furnaces. The Delhi pillar is something else entirely. It is a masterpiece of purity and accidental chemistry. Scientific analysis reveals its secret recipe. The iron is remarkably pure, with an unusually high phosphorus content and very low amounts of sulfur and manganese. This specific combination is the key. When the pillar's surface is exposed to air and moisture, the phosphorus aids in the formation of a thin, stable film of iron hydrogen phosphate hydrate. This invisible shield, called a passive layer, adheres strongly to the metal beneath and protects it from the corrosive reactions that would normally turn iron into flaky red rust. It is a self-healing barrier, a natural armor forged into the metal itself. The staggering achievement is that this was accomplished without any modern understanding of chemical formulas or electrochemical processes. The ancient Indian, working with traditional bloomery furnaces, somehow consistently produced iron with this perfect, protective impurity profile. It suggests a centuries-long tradition of empirical refinement, where techniques for selecting ores, managing furnace temperatures, and forging the metal were honed to an instinctual level. The forging of the pillar itself is another marvel. It was likely created by hammer welding together multiple masses of hot iron, a process requiring immense skill to avoid introducing flaws or weak points in a column of such size. To replicate it today would mean abandoning our controlled electric arc furnaces and precise alloy additives. We would have to return to those ancient, variable methods, and through trial and error spanning generations, somehow arrive at the exact same metallurgical sweet spot. The Iron Pillar of Delhi, therefore, is more than an object. It is a testament to a different path to knowledge, where deep observation and practiced tradition could yield results that appear, to our modern eyes, almost like magic. It poses a quiet, enduring question. How many other such perfect material recipes, discovered through generations of patient work, have been lost because we replaced artisan intuition with industrial standardization? The mastery of material, whether stone or iron, reveals an intimate dialogue with nature. But another civilization achieved a feat of engineering on the scale of the landscape itself. The temples of Angkor rise from the Cambodian jungle like a dream of stone, yet their true wonder lies not in what stands above, but in what flows beneath. Angkor Wat is merely the crown jewel of a vast, invisible machine, the hydraulic heart of the Khmer Empire. This was not just a collection of temples, but the largest pre-industrial city on Earth, a metropolis sustained by an artificial water network of breathtaking ambition. For 6 centuries, Khmer engineers orchestrated the entire monsoon cycle, turning a climate of punishing extremes into a controlled, life-giving system. Their creation was a symphony of water, earth, and spirit. They constructed massive reservoirs called, some so vast they resemble inland seas. The West Reservoir stretches 5 miles long and over a mile wide, holding millions of gallons of water, all excavated and contained by hand. An intricate lattice of canals, channels, and moats connected these reservoirs to rice paddies, to residential districts, and to every temple complex. This system served 3 profound purposes. Practically, it captured the torrential monsoon rains, preventing catastrophic floods, and then released that water during the grueling dry season to irrigate crops and sustain a population that may have exceeded 1 million people. For transportation, these canals formed liquid highways, moving people, goods, and the massive stone blocks for construction across the empire. Symbolically, and perhaps most importantly, the entire network mirrored the Hindu cosmology of the universe. The central temple mountain represented Mount, the axis of the world, surrounded by the concentric moats and reservoirs that symbolized the cosmic oceans. The Khmer did not just manage water, they architectured their spiritual beliefs into the very hydrology of their kingdom. Modern engineers, with earth-moving machines and computer models, could certainly dig a canal or build a dam of similar size. What we struggle to replicate is the holistic, integrated systems thinking behind it. This was engineering as a total philosophy, where urban planning, agriculture, religion, and ecology were inseparable components of a single design. For centuries, the full extent of this managed landscape remained hidden, with the jungle reclaiming its canals and ponds. Only recently, with the eyes of LiDAR technology, laser scanning from above that pierces the dense canopy, have we seen the staggering truth. The scans reveal a sprawling, planned grid of canals, house mounds, and small community temples extending far beyond the known temple cores, confirming Angkor as a vast, low-density hydraulic city. The achievement is humbling. It represents a long-term vision that planned not for decades, but for centuries, a testament to a society that understood its survival depended on a harmonious, engineered balance with the forces of water. Their legacy is a question written across the landscape. How do you build a civilization not just in an environment, but as an extension of it deep beneath the island of Malta? The Earth holds a different kind of blueprint. The Hypogeum is not a structure built upward, but one carved downward, a labyrinth of chambers and passages excavated from solid Globigerina limestone over 5,000 years ago. This was a sanctuary, a ceremonial space, and a memorial site, used over many centuries by a Neolithic culture whose name we do not even know. While its scale is impressive, the true engineering marvel here is not seen, but heard. In a specific chamber known as the Oracle Room, sound behaves in a way that feels supernatural. A male voice speaking or chanting at a certain pitch, around 110 Hz, causes the entire room to come alive. The sound amplifies, vibrating through the stone with a palpable physical force that resonates in your chest. The effect is not an accident of geology, but a product of astonishingly precise design. The chamber's walls are carved into smooth, curved forms. A small niche, shaped like a speaker cabinet, is built into one wall, and a word spoken into this niche does not just echo, it projects clearly throughout the entire underground complex, as if the stone itself were whispering directly into distant rooms. Modern acoustic engineers who have studied the Hypogeum confirm its properties, mapping how specific frequencies are enhanced while others are dampened. This is sophisticated sound wave manipulation, achieved before the science of acoustics was formally established. The mystery is profound. How did these Neolithic builders, with stone tools and no written language, understand the behavior of sound waves so intimately that they could sculpt rock to control them? Did they discover these acoustic properties through generations of patient trial and error, listening and carving again? Or did they possess a theoretical grasp of resonance and harmonics that has simply left no other trace? To replicate this feat today would require more than just digging a hole in limestone. It would mean abandoning our digital sound modeling software and our precise measuring instruments. An acoustic sculptor would have to start with a solid block of stone and, using only hand tools, slowly hollow out a space, tuning it by ear over years, perhaps over lifetimes, until the rock sang at the exact desired frequency. This was engineering not just of space, but of experience. The resonance likely played a central role in rituals, the vibration itself perhaps intended to induce specific states of awareness or to create a sense of a divine presence filling the chamber. The Hypogeum stands as a testament to an ancient intelligence that perceived the world in a deeply holistic way, where architecture, sound, and ceremony were threads of a single fabric. It challenges our linear view of progress, suggesting that some forms of knowledge are not cumulative, but can arise, reach a sublime peak, and then fade back into silence, leaving behind only a hollowed stone that still hums with their memory. The resonance of carved stone gives way to the rumble of carts on a grid that shaped a continent. The Roman Empire's true skeleton was not its marble monuments, but the relentless, practical lines of its roads. This was engineering on a continental nervous system, a network exceeding 250,000 miles that bound together 3 continents from the misty highlands of Scotland to the deserts of Syria. The Romans did not merely lay paths, they imposed order on the wilderness with a standardized, almost industrial precision that modern highway engineers still study with respect. Their process was in foresight and durability. First, surveyors, using simple but ingenious tools like the foresighting straight lines, would plot a route that topography, aiming for the most direct path possible. Then, laborers would dig a trench several feet deep. Into this trench, they built a road like a layered cake designed to last. At the bottom went a foundation of large stones for stability. Above that, a thick layer of rubble and gravel for drainage. Next came the nucleus, a mixture of sand and lime that acted like a primitive concrete, binding everything together. Finally, the surface, the dorsum, was paved with carefully fitted flat stones, often polygonal blocks of hard basalt or granite. But the genius was in the subtle details. Each road was gently cambered, arched from the center down to the edges, so rainwater would run off into drainage ditches alongside, preventing the washouts that plague flat paths. The result was a road surface so hard and stable that it could support the constant passage of armies, trade caravans, and imperial messengers for centuries, and many of them do. Across Europe and the Middle East, you can still drive on the original Roman paving stones, or walk along roadbeds that have outlasted every empire that followed. Modern asphalt, by contrast, is a marvel of speed and economy, laid by machines in days. Yet it cracks under frost, softens in heat, and requires resurfacing every decade or two under heavy use. To build a Roman road today, with its deep, multi-layer construction and hand-fitted stone surface, would be astronomically expensive and slow. It would require a return to armies of manual laborers and a willingness to invest not for the next fiscal quarter, but for the next 1,000 years. The Roman road was not a temporary convenience, it was a permanent claim. It whispered a promise of unshakable order, that no matter how far you traveled from the capital, you were still walking on Rome. This network did more than move legions. It transmitted ideas, languages, and culture at the speed of a marching man, forging a unified world from a mosaic of tribes. Its endurance poses a quiet challenge to our own philosophy of infrastructure. Have we, in our pursuit of speed and lower cost, forgotten how to build things meant to outlive us, yet the Romans built for the surface of the earth, while another culture seemed to work with a different set of rules entirely, rules that suggest a mastery over solid stone that defies simple explanation. Deep beneath the sands of Saqqara, in a long, silent corridor known as the rests a collection of objects that should not exist. Here are 24 colossal sarcophagi, each carved from a single, immense block of incredibly hard stone, like rose granite or diorite. Their scale is the first shock, each one weighing between 60 and 100 tons, the weight of a large locomotive. But it is their interior that stops engineers and archaeologists cold. Each of these mammoth boxes has been hollowed out. The inside surfaces are flawlessly smooth, with corners so sharp and precise they look as if they were cut by a giant mechanical milling machine. The surfaces are polished to a mirror-like sheen, and the massive lids, themselves ton slabs of stone, fit onto their bases with a seamless join that is virtually invisible. This is precision on a monumental scale, achieved in one of the hardest materials on Earth. The mystery is not just what they built, but how they could have possibly built it with the tools we know they had. The conventional explanation involves a slurry of wet sand and a copper saw or drill. Sand contains quartz, which is harder than granite, so with enough time and pressure, the abrasive slurry could theoretically grind through the stone. But the scale here changes everything. To hollow out just one of these 100-ton boxes, using a handheld copper tube drill in sand, would require not just patience, but an application of sustained, immense downward pressure that seems physically implausible. Some calculations suggest it would take generations of continuous, 24-hour drilling to achieve just one sarcophagus. Furthermore, the tool marks left inside some of these boxes show clean, consistent spirals and grooves that look remarkably like the feed marks of a modern core drill, not the erratic, wobbly scratches one might expect from a hand-powered, abrasive process. This has led to a heated and enduring debate. Did the ancient Egyptians possess a lost technology, perhaps a mechanical means of applying tremendous, steady force? Could they have used tools tipped with something harder than copper, like emerald or specially treated diamonds, materials we have simply not found in the archaeological record? Or does this represent the absolute pinnacle of what is possible with simple tools, pushed to a limit we can scarcely comprehend? A testament to a society that was willing to devote centuries of skilled labor to a single, sacred project. Modern diamond-tipped coring drills can, of course, replicate the cut. But that is the point. We need industrial technology to match what they appear to have done. The boxes stand as silent, polished arguments in stone. They do not tell us their secret, they only present us with a finished product of impossible perfection, forcing us to question the very timeline of human ingenuity. Were they the product of an advanced, forgotten technique, or simply the ultimate expression of an ancient art form where time itself was the most abundant tool while stone sarcophagi stand rigid? Another ancient solution to nature's violence was to build something that could dance. In the land of the rising sun, where the earth trembles with relentless frequency, wooden pagodas have performed a silent, swaying ballet for well over 1,000 years. The pagoda, built in the 7th century, is the oldest surviving wooden building on Earth, and it has weathered countless powerful quakes that have flattened modern cities. Its endurance is no accident of location, but the result of a profound, intuitive understanding of how to live with instability. The secret lies in a design philosophy that embraces flexibility over brute strength. At the heart of the pagoda, running up through its center, is a massive free-hanging pillar called the. This is the genius of the structure. Unlike a modern skyscraper's steel core, this central pillar is not firmly attached to the building at every level. Instead, it acts like a giant, weighted pendulum. When an earthquake strikes, the flexible wooden frame of the pagoda begins to sway in one direction. The heavy, suspended within, lags behind, swinging in the opposite direction. This counter motion absorbs and dissipates the seismic energy, preventing the building from resonating to a destructive frequency. It is a passive damping system carved from a single tree. Surrounding this brilliant core is another marvel of joinery, the complex bracket systems known as Tokyo. These interlocking wooden brackets, assembled without nails in the core structure, are not rigid locks. They are carefully crafted connections that allow for a controlled amount of slippage and movement. During a tremor, the entire pagoda behaves like a flexible spine, with each floor able to sway independently, sliding slightly over the one below. The energy is not resisted. It is gracefully passed through the structure and harmlessly dispersed. Modern engineers achieve a similar effect in skyscrapers with high-tech tuned mass dampers, enormous counterweights installed at the top of a building that slide on oil films or pendulums to counteract sway. The ancient Japanese carpenters, however, baked this damping principle into the very soul of the building using only wood, joinery, and a deep empirical knowledge of dynamic loads. Replicating this today is not a question of lacking the technical know-how, but of embracing a completely different philosophy. Our modern construction instinct is to create rigid monolithic strength, to bolt everything down and fight the force. The pagoda builders understood that to win, you must yield. To build a true replica would require abandoning steel reinforcement and concrete cores. It would demand master craftsmen who can shape wood joints with tolerances that allow for movement without failure, and the patience to grow and select timber with the perfect grain and flexibility. It is organic engineering, where the building is not a static object, but a living, responsive system. These pagodas stand as serene monuments to resilience, whispering that sometimes the strongest response to an unstoppable force is not to stand rigid, but to learn how to sway. Deep beneath the rolling plains of Cappadocia, an entire civilization once turned its back on the sun. The city of is not a ruin on a hill, but a void within the earth, an 18-story deep labyrinth carved from soft volcanic rock called tuff. This was not a temporary refuge or a simple cave network. It was a fully realized, subterranean metropolis, engineered to sustain up to 20,000 people for months at a time. To descend into its depths is to walk through an underground survival, a negative space meticulously planned for permanent life. The initial challenge was one of pure stability. Carving deep into rock requires an intuitive understanding of load bearing, of where to place supporting pillars and arches to prevent catastrophic collapse. The builders of, likely beginning in the early centuries of the Common Era and expanding over generations, navigated this with astonishing skill, creating stable, level galleries, staircases, and communal rooms. But the true stroke of genius was in the invisible systems. A city of 20,000 people, sealed underground, would suffocate in hours without fresh air. The engineers solved this with over 50 ventilation shafts, some plunging over 170 feet straight to the surface. These acted as the city's lungs, creating a passive airflow system where cooler, denser air from the surface would sink down the shafts, displacing the warmer, stale air inside and forcing it up and out through other passages. It was natural air conditioning, engineered through geometry. Water was supplied by deep, protected wells, tapping into the same groundwater table that served the surface world. There were spaces for livestock, wineries, kitchens with carved hearths and chimneys that vented smoke without revealing the city's location, and even chapels with vaulted ceilings. The security system was both simple and formidable, massive, circular stone doors, each weighing up to half a ton, that could be rolled across key passageways from the inside, sealing entire sections off from intruders. Modern tunnel boring machines could, of course, carve out a cavity of similar volume in the soft tuff. But that is merely excavation. The miracle of is its holistic, anticipatory design. Every need for a functioning society, from air and water to worship and waste management, was preemptively solved in a three-dimensional, lightless space, all carved by hand with hammers, chisels, and an immense foresight. It represents a radical engineering philosophy, one that looked at the landscape not for what could be built upon it, but for what safety could be carved from within it. This was not a retreat, but a deliberate alternative way of urban life, a testament to a community that planned not just for the next harvest, but for the next invasion, the next crisis, with a depth of preparation that feels almost prescient. In its cool, silent halls, we find a different kind of monument, one that speaks not of reaching for the heavens, but of the profound resilience found in turning inward and building a world in the dark. From the dark, cool refuge of underground cities, we emerge into a landscape of blistering sun and sudden floods, where another civilization performed a different kind of alchemy. They turned the very earth beneath their feet into towers that scraped the desert sky. In the valley of Yemen, the ancient walled city presents a sight that defies expectation. Rising abruptly from a rocky plateau, its densely packed towers, some reaching 11 stories high, have earned it the name the Manhattan of the desert. These are not monuments of stone or steel, but skyscrapers of mud. For over 5 centuries, these structures have stood against a punishing environment, a testament to an engineering tradition that mastered a material most of us consider fragile and temporary. The primary substance is adobe, a simple mixture of sun-dried mud brick, reinforced with chopped straw. To the modern eye, building a towering apartment block from mud seems almost reckless. Yet here they are, homes for thousands, enduring where many modern reinforced concrete buildings in similar climates crack and fail within decades. The secret is not in a single innovation, but in a holistic system of design born from centuries of lived experience. The walls themselves are the first clue. They are massively thick at the base, sometimes over 6 feet wide, and they taper gracefully as they rise. This shape provides a stable, weighted foundation that resists toppling in high winds while reducing the load on the upper floors. The mud mixture is a precise recipe. The straw acts as a binding agent, providing crucial tensile strength to prevent the bricks from cracking as they expand and contract with wild temperature swings. But the true genius is in the maintenance cycle, an integral part of the design itself. After the rare but violent flash floods that surge through the valley, the lower portions of the towers are often coated with a fresh layer of mud plaster. This is not a sign of decay, but of renewal. Each application repairs minor erosion and strengthens the structure for the next generation. The knowledge of exactly how to mix the plaster, when to apply it, and how to manage the intricate network of drainage spouts and protective foundations is a living craft, passed from parent to child. Modern engineers attempting to build tall with adobe often find themselves forced to add steel rebar or concrete frames, fundamentally changing the material. To build as the people have did, using only local earth, water, and organic fiber, and to achieve such height and longevity requires surrendering our standardized code books. It demands a deep, intuitive dialogue with the material, an understanding of how this specific mud from this specific wadi behaves in the summer heat versus the winter chill. The towers are not frozen artifacts, they are living architecture, constantly being remade by the hands of their inhabitants. They represent a form of engineering where the blueprint is not a static document, but a cultural rhythm, a seasonal ritual of care woven directly into the fabric of daily life. In their silent, dusty grandeur, they ask a profound question of our own throwaway construction culture. What if resilience was not about building something that never needs repair, but about building something whose repair is a sacred, sustaining tradition? The solidity of earthbound towers dissolves into the fluid, trackless expanse of the world's largest ocean. Here, the greatest engineering feat was not a monument, but a journey, a story written in the paths of stars and the rhythms of the sea. The Polynesian voyagers settled the Pacific, finding and populating specks of land scattered across 10 million square miles of open water, a triangle from Hawaii to New Zealand to Easter Island. They did this in vessels that seem impossibly humble by modern standards, double-hulled sailing canoes called, lashed together with intricate cordage. But their true masterpiece was not the canoe itself, though its flexible, lashed construction was a brilliant adaptation to ocean waves. Their supreme engineering achievement was an invisible one, a vast, living library of environmental knowledge encoded in memory and tradition, a system we now call wayfinding. Without a single compass, sextant, or chart, these master navigators could set out on a voyage lasting weeks and reliably find an island target sometimes no larger than a pinprick on the horizon. Their instruments were the natural world itself, read with a precision we have almost entirely outsourced to machines. They memorized the precise rising and setting points of over 200 stars, creating a celestial compass that turned the night sky into a fixed map. By day, they read the ocean itself. They learned to distinguish the subtle, refracting patterns of swells that bounced off distant islands, feeling the way the canoe moved beneath them to detect land far beyond the visible range. They watched the flight paths of specific seabirds, knowing which species would fly out to fish in the morning and return to land at night, revealing its direction. They interpreted the color and shape of clouds, which often gather or take on a greenish tint over the lagoons of low-lying atolls. This was not a collection of separate tricks, but a holistic, integrated cognitive system. A master navigator, or kahuna, would often conduct a voyage from a small, enclosed hut in the center of the canoe, deprived of visual landmarks, navigating solely by the feel of the swells against the hull and the position of the stars through a small opening. They held a mental model of the ocean's dynamic currents, the seasonal winds, and their own position within this living system, constantly updating it without writing down a single note. Building a traditional today is a complex but achievable task of craftsmanship. The true replication challenge lies in the mind. Modern sailors, even expert ones, are conditioned by technology. We rely on GPS to tell us exactly where we are, a constant stream of data that ironically can dull our innate senses. To truly replicate the Polynesian feat means to unlearn that dependency. It means spending years, perhaps a lifetime, apprenticed to the sea and sky, developing a sensory awareness and a memory capacity that our digital tools have rendered almost obsolete. It is the engineering of human perception itself, turning the navigator into a living, breathing supercomputer processing environmental data in real time. This knowledge was nearly lost, preserved only in a few lineages and cultural memories. Its modern revival is not just about rebuilding canoes, but about reclaiming a relationship with the world that is based on profound, participatory observation. The voyagers did not conquer the Pacific, they conversed with it, and in that endless dialogue, they engineered the most reliable navigation system ever devised, one made entirely of knowledge, courage, and attention. The ocean's vastness demanded not just navigational genius, but a material that could stand defiant against its endless, corrosive power. While the Polynesian voyagers mastered crossing the water, another civilization performed a different miracle. They built structures to become a permanent part of the sea itself. Along the Mediterranean coast, ancient Roman harbors still lie submerged, their concrete piers and breakwaters, intact after 2,000 years of relentless waves. Modern concrete, by stark contrast, often begins to weaken and crack in marine environments within mere decades. The Roman material did not just endure, it thrived, actually growing stronger with age, a property that seems to defy the very laws of material decay. This was not a lucky accident of chemistry, but the result of a specific, lost recipe for a self-healing stone. The Romans called their magical ingredient pozzolana, a fine volcanic ash mined from regions like When mixed with lime and seawater, this combination triggered a chemical reaction that modern scientists have only recently begun to fully decipher. The secret lies in what happens long after the concrete is poured. When seawater seeps into the Roman mixture, it slowly reacts with the volcanic ash and lime to form extremely rare, plate-like minerals, including one called aluminous. These crystals are not a sign of degradation, they are a regenerative armor. As tiny cracks inevitably begin to form from the stress of waves, the ongoing chemical process causes these minerals to grow precisely within those fissures, effectively gluing them shut from the inside out. The concrete does not merely resist the sea, it incorporates the seawater into its own repair mechanism. Modern Portland cement concrete works on a completely different principle. It sets through a rapid, one-time reaction that creates a brittle matrix. Seawater infiltrating this matrix can corrode the steel reinforcement bars inside and cause expansive crystals to form, which actually push the concrete apart from within. We fight this decay with costly sealants and constant maintenance. The Romans, with no knowledge of nanoscale chemistry or crystalline structures, engineered a material that maintained a dynamic, centuries-long conversation with its environment. Today, teams of material scientists are actively trying to reverse engineer the exact Roman formula, conducting experiments with volcanic ash and different mixing protocols to unlock its secrets for our own crumbling ports and nuclear waste containment structures. The irony is profound. We possess electron microscopes and molecular modeling software, yet we are struggling to intentionally recreate what the Romans achieved through generations of empirical trial and error, finding a perfect local material and a mixing process that yielded what we can only describe as a living stone. Their harbors stand as a quiet, wet challenge, proving that sometimes the most advanced engineering is not about forcing nature to obey, but about learning the recipe that lets your creation become one with it. The concept of a living stone that repairs itself finds a strange echo in a high desert canyon, where light itself was engineered into a calendar. Atop the towering Butte Canyon, the ancestral people, sometimes called the Anasazi, performed a feat of astronomical precision that required no moving parts, only a profound understanding of the sun's slow dance across the sky. Behind three colossal, carefully positioned stone slabs, they carved a spiral petroglyph into the cliff face. This was not random art. It was a target. On the summer solstice, a dagger of sunlight pierces the center of the spiral. On the winter solstice, two perfect shafts of light bracketed on either side. During the equinoxes, another light dagger slices directly through the center of a smaller, adjacent carving. This solar calendar, created over 1,000 years ago, marks the turning of the seasons with a reliability that rivals any modern timepiece. The staggering aspect is the deliberate engineering behind this seemingly natural phenomenon. Those three slabs, each weighing several tons, were not randomly placed by erosion. Archaeologists have found clear evidence that the ancestral painstakingly chipped and shaped them, then leveraged them into a very specific position. This was not a matter of simply rolling a few boulders. It was the calculated placement of a massive stone aperture, a natural lens designed to filter sunlight into a precise, predictable pattern. To achieve this, the builders needed more than strength, they needed generations of patient observation. Someone, or more likely a lineage of sky watchers, had to spend years, perhaps decades, noting exactly where the sun's light fell on that cliff face at different times of the year. They had to internalize the solar cycle so completely that they could predict where a beam would strike not just next year, but for centuries to come. Then, they had to translate that immaterial knowledge into a physical intervention, moving mountains, or at least ton slabs, to capture that beam forever. Replicating the sun dagger today with modern machinery is straightforward in theory, but misses the point entirely. We could use a crane to place the slabs, a laser to align them, and a computer to model the sun's path. But that would be our knowledge, imposed on the landscape. The true replication challenge is to step away from the technology and enter the mindset of the original engineers. It would require a community willing to dedicate a lifetime to watching a single sunbeam crawl across a rock, to see time not as numbers on a dial, but as a living line of light etched by a star. It was an engineering of knowledge, where the final, brilliant alignment was merely the physical expression of a deep cultural cosmology, a way of weaving the rhythm of the heavens directly into the very bones of the earth. This was not a tool for telling time, but a sacred mechanism for synchronizing human life with the cosmic order, a silent, stone clock that ticks just once a year. The silent stone calendar measured celestial time, but another ancient structure was built to control the flow of human history itself. Stretching over 13,000 miles across the most unforgiving landscapes on Earth, the Great Wall of China is often misunderstood. Its true engineering marvel is not found in a single, uniform barrier, but in its breathtaking adaptability. This was not a single project, but a long campaign of construction, with the most famous sections built by the Ming Dynasty. Their achievement was an organizational miracle, a feat of logistics and management on a scale that dwarfs even the most ambitious modern megaprojects. The wall had to traverse everything from jagged mountain peaks and steep ridges to vast, wind-scoured deserts and rolling grasslands. The Ming engineers did not impose a single design upon this chaos. They allowed the land to dictate the solution. In the Rocky Mountains, they local stone to build towering, formidable battlements. Across the arid western deserts, where stone was scarce, they used layers of tamped earth and gravel, compacted into a dense, resilient mass that could withstand centuries of erosion. They built with what was under their feet, turning the very terrain into a defense. But the material ingenuity is only half the story. The placement of tens of thousands of watchtowers reveals a sophisticated understanding of communication and control. These towers were not spaced at random intervals. They were positioned at optimal visual distances, often within sight of one another, so that signals, whether by smoke by day or fire by night, could relay a message across hundreds of miles in a matter of hours. This created a nervous system for the empire, a way to coordinate military response across a frontier longer than the continent of Africa. The logistical challenge of sustaining this effort is almost incomprehensible. For over 2 centuries, the Ming Dynasty coordinated millions of workers, soldiers, and artisans across this vast, remote frontier. They had to feed these armies, supply them with tools, and manage the construction of fortresses, barracks, and granaries, all without telephones, railways, or motorized transport. Orders from the capital could take weeks to reach the distant work sites. This required a decentralized system of immense trust and local authority, where regional commanders had to solve problems on the ground with the resources at hand. Modern engineering could certainly build a physical wall of similar length, using drones for surveying and machinery for moving earth. But replicating the Ming achievement means abandoning our digital networks and global supply chains. It means coordinating the labor of millions of people across a wilderness, motivating them, housing them, and directing their work with nothing but handwritten scrolls, messengers on horseback, and a shared, unwavering imperial vision. The wall was more than a military barrier. It was a statement of administrative power, a symbol of cultural separation, and a managed corridor for trade and migration. Its scale is not just in its bricks and mortar, but in the monumental act of human will it represents, a collective effort so vast it became the only human-made structure visible from the vague vantage of low Earth orbit. It stands as the ultimate testament to pre-modern project management, asking us what we could possibly organize today if our tools were reduced to paper, persuasion, and the patient labor of countless hands. The ambition to control a frontier dissolves into the palm of the hand, where time itself was miniaturized into a pocket universe of bronze. In the 6th century, a Byzantine craftsman created a portable sundial, a device that fits comfortably in your hand, yet within its compact case lies a complexity that echoes the ghost of the mechanism. This was not a simple shadow caster. It was a personal astronomical computer, its face a maze of intricate scales, and its heart a tiny assembly of precisely cut bronze gears. By aligning the device with the sun and turning a dial, the owner could not only tell the hour, but also calculate the date, track the zodiac, and even adjust for the user's specific latitude on journeys across the empire. It translated the grand motions of the cosmos into a personal, mechanical poetry. The discovery and study of devices like this have profoundly reshaped our understanding of ancient engineering. They prove there was not a miraculous, solitary anomaly, a single flash of genius lost at sea. Instead, it appears to have been part of a sustained, sophisticated tradition of precision instrument making, a craft that spans centuries and empires. The Byzantine sundial is its smaller, more refined cousin, evidence that the knowledge of geared computation was kept alive, passed down through workshops, and adapted for both practical and scholarly use. The craftsmanship required to produce it is humbling. Each minuscule gear, some no larger than a pea, was hand-filed from a sheet of bronze. Their teeth had to be shaped and spaced with geometric consistency to ensure they meshed and turned without binding, a task demanding the steady hand and keen eye of a master artisan. This was more than metalworking. It was a fusion of advanced astronomy, practical mathematics, and microscale engineering, all achieved without optical magnifiers or electric tools. Today, computer-controlled micromachining can produce 1,000 perfect replicas in an hour. But that ease of production obscures the true marvel. In the Byzantine world, each of these devices was a unique masterpiece, the product of a specialized, high artisan culture where knowledge was embodied in skill, not just in diagrams. Creating one was an act of profound concentration, where the margin for error was vanishingly small and the materials were unforgiving. This tradition represents a different path for technology, one not aimed at mass production or industrial scale, but at the exquisite refinement of knowledge into a portable, personal object. Its existence suggests a quiet, continuous thread of high mechanical art, weaving from the Hellenistic workshops through the Byzantine Empire, and perhaps influencing later Islamic and European instrument makers. These delicate bronze gears, turning in the sunlight, whisper that some of history's most advanced engineering was not always monumental in scale, but could be held in the hand, a secret calculus of the heavens crafted for a single, curious mind. While personal instruments calculated the heavens, a different kind of experiment was taking place in a colossal earthen bowl. In the highlands near, the Inca engineered not a building, but a climate. The site of Moray is a breathtaking sight, a series of enormous circular terraces, like giant stone amphitheaters carved deep into the ground. The largest of these depressions plunges over 150 feet from the rim to the floor, with concentric rings of perfect stone walls holding back the earth. This was far more than a beautiful quarry or a ceremonial space. Walking from the top terrace down to the bottom, the air changes noticeably, growing cooler and more still. Researchers have measured a temperature difference of up to 27 degrees Fahrenheit from the highest ring to the lowest. This was not an accident of geography, it was the entire point. Moray is now widely believed to have been a vast agricultural laboratory, a living test tube for the Inca Empire. The engineering here served a profoundly intelligent purpose, the domestication of the landscape itself. Each terrace, with its precise stone retaining wall, created a stable, flat platform for soil. But the genius was in the system. Intricate irrigation channels fed water to each level, while a sophisticated network of drainage stones and gravel layers beneath the soil prevented the entire bowl from flooding and turning into a muddy pond during heavy rains. This control over water was matched by a manipulation of air. The circular, sunken design created distinct microclimates. The bottom, sheltered from wind and receiving less direct sunlight, mimicked the cooler conditions of higher altitudes. The top rings experienced more sun and wind, replicating lower, warmer valleys. This allowed Inca agriculturists to conduct experiments on a grand scale. They could test which varieties of maize, potatoes, or quinoa thrived in which thermal zone, effectively acclimatizing crops to different elevations without having to transport them across dangerous mountain passes. They could simulate the conditions of newly conquered territories right here in the imperial heartland, de-risking agriculture and securing the food supply for millions. Modern agronomists look upon Moray with a sense of awe. We have climate-controlled greenhouses and sensor networks that monitor soil moisture and temperature in real time. The Inca achieved a similar gradient of environmental conditions using only stone, water, and a masterful understanding of solar geometry and hydrology. They engineered an entire ecosystem, turning a natural depression into a calibrated instrument for biological research. Replicating this today with machinery would be simple. We could excavate a big hole and line it with concrete. But to do it, as the Inca did, to read the land so perfectly that you could sculpt it into a functioning laboratory for life, required a knowledge that was both granular and holistic. It was bioengineering centuries before the term existed, a testament to a civilization that saw the environment not as a challenge to overcome, but as a complex, living system to be carefully understood and respectfully harnessed. Their greatest crop may not have been a grain, but knowledge itself, cultivated layer by layer in a sacred, stone-ringed earth. The earth itself could be sculpted into a laboratory, but in the forests of West Africa, fire and metal were coaxed into telling a kingdom's history. In the Kingdom of Benin, what is now modern Nigeria, artisans from the 13th century onward performed a kind of alchemy. They transformed brass and bronze into breathtaking narratives, producing thousands of plaques and sculptures that recorded court life, myth, and power. Their medium was metal, but their true engineering feat was the flawless execution of a process called lost wax casting, or sire, on a staggering scale and level of detail. This was not simple metalworking. It was a controlled, chemical ballet performed in a clay mold. The process began with a core of clay, shaped roughly like the desired final object. Over this core, the artisan would build up a precise model using beeswax, sculpting every minute detail, every feather in a headdress, every link in a chain, every expressive line in a face. This wax model was then encased in a thick layer of fine clay, forming the investment mold. Small clay channels were added for air to escape and for molten metal to pour in. The entire assembly was then baked in a furnace. This was the critical moment of transformation. The heat melted the wax, which drained out through the channels, leaving a perfect hollow negative space inside the hardened clay mold, a cavity capturing every nuance of the original wax sculpture. Then molten bronze, heated in a crucible to over 1,000 degrees Celsius, was poured into that empty space, filling the intricate void. Once the metal cooled and the outer clay mold was broken away, revealing the metal object within, which was then cleaned, polished, and sometimes gilded. The genius of the Benin brassmiths lay in their absolute mastery of every variable in this delicate chain. They had to formulate clay that could withstand thermal shock without cracking. They needed to calculate the exact thickness of the wax walls to ensure even metal flow and cooling, preventing flaws or weak spots in the final piece, especially for large, thin plaques. They engineered their furnaces, likely using charcoal and bellows, to reach and maintain the precise temperatures needed to melt the copper and tin alloy without burning it. And they did this not just once, but thousands of times, producing works of consistent, museum-quality sophistication. Modern art foundries use electric kilns, pre-mixed investment plasters, and digital temperature controllers to achieve similar results. The Benin masters worked with local materials, handmade tools, and an empirical knowledge refined over centuries and protected within guilds. This was engineering in service of art and statecraft, a metallurgical tradition so advanced it allowed a civilization to cast its own memory in enduring metal. Each plaque is a frozen moment, but the process that created it is a testament to a different kind of intelligence, one where chemistry, thermodynamics, and artistic vision were unified into a single, sacred craft. The mastery of stone speaks a universal language, and on the windswept island of Sardinia, it rises in a chorus of silent, conical towers. Scattered across the landscape like stone sentinels, they are the defining mystery of the civilization, a people who flourished for over a millennium beginning nearly 4,000 years ago. They built not one or two, but an estimated 7,000 of these unique structures, creating a networked stone spine for their entire society. Walking among the ruins of a complex like, you are struck not by ornamentation, but by a profound, rugged logic. These are beehive-shaped fortresses and dwellings built entirely without mortar, using massive, rough-hewn blocks of local basalt. The technique is one of pure balance, where each stone's weight and placement is the only thing holding the entire tower together. This is dry stone construction pushed to an architectural extreme. The true engineering marvel lies in the ceiling, in what is known as a corbelled dome. Instead of using arches or a central keystone, the builders created a dome by laying each successive ring of stones so that it slightly overhangs the one below, gradually narrowing the circle until the final capstone closes the opening at the top. It is a process that looks deceptively simple, like stacking coins in a narrowing spiral, but with multi-ton blocks of stone, the margin for error is zero. Each block must be chosen and shaped with an intuitive understanding of compression forces. The weight of every stone is channeled diagonally downward through the structure, transferring the load into the thick, tapering walls and ultimately into the ground. A single miscalculation, one block placed with its center of gravity too far out, would create a point of weakness that could cause the entire dome to buckle inward under its own mass. The builders possessed this intuition at a cultural scale. The sheer number of, many still standing after 3 of weather and earthquakes, tells us this was not the secret knowledge of a few elite masons. It was a standardized, widespread craft, a common language of stone known across the island. This suggests a society where engineering principles were deeply embedded in daily life, passed down through generations, until constructing a stable, mortarless dome became as fundamental a skill as planting a crop. Modern stonemasons can and do replicate corbelling techniques, often for garden walls or historical restoration. But to replicate the achievement means to envision an entire civilization where this demanding, time-consuming method was the default way to build homes, watchtowers, and communal gathering places. It represents a collective commitment to permanence and local materials, a choice to work in harmony with the landscape's volcanic bones rather than to impose a foreign technology upon it. The silent, therefore, are more than ruins. They are a testament to a society that found its strength and its identity in a perfect, balanced fit, where the security of the community literally rested on every citizen's understanding of how to make stone hold stone. While stone towers embodied static strength, the workshops of Hellenistic Alexandria were alive with motion and sound. Here, in the great library's shadow, engineers turned water, air, and steam into pure theater. Ancient texts describe a palace filled with wonders that seem plucked from myth, mechanical birds that sang on command, automatic servants that poured wine for guests, and doors that swung open as if by magic, all powered by hidden forces. These were the hydraulic automata, and they represent a startling detour in the history of technology, a path not toward utility, but toward wonder. The most famous inventor of these devices was Hero of Alexandria. Among his many creations was the, often called the first steam engine. It was a simple, beautiful device, a sealed sphere mounted on a boiler. As water heated, steam shot out from 2 bent nozzles on the sphere, causing it to spin rapidly on its axis. It was a clear demonstration of the principle of action and reaction, the same principle that would one day propel jet engines and rockets. Yet for Hero and his contemporaries, it was not a practical engine. It was a fascinating demonstration, a temple wonder. The true engineering brilliance, however, lay in the more elaborate theatrical machines. Using nothing but systems of siphons, counterweights, valves, and gears, they could create scenes of astonishing complexity. Imagine a miniature temple where doors open automatically as a fire is lit on an altar, powered by the expansion of heated air. Or a mechanical play where figures moved across a stage, driven by a descending weight that turned a winding drum, the ancestor of all clockwork. Recreating these devices today is an exercise in straightforward engineering, a fun project for historians and hobbyists. We have precise pumps, plastic tubing, and digital controllers to manage the sequences. The staggering fact is that the original inventors had none of this. They started from the bare first principles of physics, from observing how water seeks its own level in a siphon, how heated air expands, how steam creates pressure. They then engineered those simple observations into elaborate, narrative-driven spectacles purely for the sake of intellectual delight and royal entertainment. This is what makes their achievement so poignant and so profound. They possess the foundational knowledge for automation, for mechanical power, even for steam propulsion, centuries before an economic or industrial context existed to demand such things. Their creativity was unleashed not by necessity, but by curiosity and a desire to inspire awe. It was engineering as a form of philosophy and art, a playful exploration of nature's hidden levers. The path not taken here is one of history's great what-ifs. What if this culture of inventive play had been coupled with a drive toward widespread practical application? The answer, perhaps, is that the mindset was fundamentally different. Their genius was in asking, can we make this happen? Not what can this do for us? In their singing bronze birds and spinning steam spheres, we see a flash of pure, unharnessed potential, a brilliant engineering creativity that chose, for a few centuries, to build dreams instead of industry. It reminds us that innovation is not always a linear march toward efficiency. Sometimes it is a dance of ideas, performed for its own beautiful sake. The playful ingenuity of automata reveals a world of hidden mechanics, but in the desert canyons of Jordan, an entire civilization performed a different kind of magic. They did not assemble, they revealed. The city of Petra is not built upon the landscape. It is the landscape itself, painstakingly excavated from the living rock. They were masters of subtractive engineering, a discipline that demands a profound and fearless conversation with the stone. Every column, every pediment, every delicate urn that crowns the iconic treasury was not placed there. It was discovered within a solid cliff of rose-red sandstone. This process turns architectural planning completely inside out. A traditional architect imagines a void and fills it with material. The architect had to envision a magnificent void hidden inside a mountain, and then, with astonishing confidence, remove everything that was not that vision. The first and greatest challenge was reading the rock itself. Before a single chisel struck, master craftsmen had to assess the cliff face with an intuitive geology. They needed to identify solid, stable beds of sandstone, avoiding hidden fissures, weak layers, or seams that could cause a facade to crack or collapse partway through its creation. They worked from the top down, carving scaffolding and work platforms directly into the rock as they descended, a method that prevented catastrophic falls but required them to finalize the upper details before they could even begin on the lower floors. Using little more than iron chisels, picks, and hammers, teams of workers would rough out the shape, then refine it with finer tools and abrasives. The famous treasury, or Al, with its two-story Hellenistic facade, is a masterpiece of this terrifying precision. To create those freestanding columns, the masons had to carve away the tons of stone surrounding them, leaving these delicate forms attached only at the top and bottom, all while ensuring the immense weight of the cliff above was properly distributed around the newly created hollow. One misjudgment in the thickness of a wall or the angle of a load-bearing arch could have brought the entire enterprise down in a cloud of dust. Yet they succeeded, not just once, but in crafting hundreds of tombs, temples, and dwellings, each one a unique sculpture on a monumental scale. But Petra's genius is not skin deep. This city of stone was also a city of water. In a region of brutal aridity and sudden, violent flash floods, they engineered a hydraulic system as sophisticated as their architecture. They carved channels along the canyon walls to divert floodwaters, built dams to control the surge through the narrow entrance, and sculpted vast cisterns into the rock to capture and store every precious drop. This network turned a potential death trap into a life-giving oasis, sustaining a population of thousands and fueling the trade wealth that made Petra a crossroads of the ancient world. Today, with diamond-tipped saws, core drills, and ground-penetrating radar, we could certainly carve a facade into a cliff, but that would be a technical exercise in removal. To replicate the feat is to replicate a mindset. It requires the courage to commit to a plan with no option to rebuild, the patience to unfold a city over generations, and a sensory knowledge of stone that feels less like engineering and more like a form of reverence. Petra is not a ruin, it is a revelation, a testament to the belief that the most breathtaking spaces are not those we construct, but those we have the vision to set free from the heart of the mountain. The mountain's solid stone gives way to a crossing of air and fiber, a bridge that breathes with the wind. High in the Peruvian Andes, the last remaining example of an Inca suspension bridge sways gently over the river gorge. It is not a monument frozen in time, but a living tradition, a structure that dies and is reborn anew every single year. This cycle of renewal is the very heart of its engineering genius, a feat woven not just from grass, but from community itself. The Inca Empire's vast road network, over 25,000 miles of trails connecting mountain peaks and deep valleys, was useless without a way to cross the continent's countless raging rivers and dizzying chasms. Their solution was a network of these fiber bridges, and the method for building them was a masterpiece of applied knowledge. The material is a tough, resilient mountain grass. Families from 4 local communities spend months gathering and twisting the grass into thin cords, a process of patient, rhythmic labor. These cords are then braided into larger ropes, and those ropes are braided again into the massive cables that will form the bridge's very bones. The braiding technique is crucial. It creates a cable with immense tensile strength, flexible yet capable of supporting the weight of people and livestock. On a designated day, the communities gather. The old bridge is cut down, and its remains offered to the river, a ceremonial release. Then, working from opposite sides of the gorge, teams of men and women pull the new cables across using the old bridge's remains as a guide rope. The cables are anchored to massive stone abutments built centuries ago, a permanent foundation for a temporary structure. They weave the footpath and the side railings, creating a narrow, flexible walkway that dances with every step. This design, which might seem precarious, is intentional. The controlled sway allows the bridge to dissipate the energy of the fierce mountain winds that roar through the canyon, preventing the kind of rigid, harmonic oscillation that could tear a static structure apart. Modern steel suspension bridges are undeniably stronger and more permanent, but they represent a different philosophy, one of imposing a fixed, industrial solution upon a landscape. The Inca Bridge is an extension of the landscape, made entirely from renewable local materials, lightweight, and completely repairable by the people who use it. Its annual rebuilding is not a sign of primitive technology, but of a sustainable social engineering model. The knowledge of the braiding patterns, the tensioning methods, and the ritual of construction is not written in a manual. It is held in the collective muscle memory of the community, passed from elders to the young through direct participation. To replicate this feat today is not about sourcing grass rope or copying the weave. It is about replicating the social fabric. It requires a society where infrastructure is not an anonymous service provided by a distant government, but a direct, sacred responsibility of every citizen, a shared act of maintaining the literal ties that bind the community together. The bridge stands, or rather, it is constantly becoming, as a testament to a vision where engineering is not separate from culture, but is culture in action, a yearly promise woven across the void. While the Inca bridge spans a chasm with living fiber, another civilization turned the very concept of a well inside out, creating not a hole in the ground, but a palace for water. In the arid plains of western India, the ancient stepwells, known as, are monuments to a profound inversion. They are not structures that reach for the sky, but ones that descend into the earth with breathtaking grandeur. The most famous of these is a staggering geometric vision. Imagine a colossal, inverted pyramid carved into the crust of the planet. On three sides, a perfectly symmetrical cascade of stone steps, 3,500 of them, marches down 13 stories into a cool, dark abyss. On the fourth side stands a pavilion of ornate columns and carved galleries, a place for rest and ritual. This was far more than a place to fetch water. It was a sacred, engineered ecosystem, a response to a climate of extremes. The design was dictated by necessity. In a region where the water table could plunge dramatically during long dry seasons, a simple shaft well would become useless. The stepwell's genius was its staircase, which allowed people to descend alongside the receding water, always maintaining access no matter how deep it fell. But the engineering challenges were immense. Excavating such a vast, open pit without modern shoring required an intuitive mastery of soil mechanics. The builders had to shape the walls with a precise batter, angling them inward to counteract the immense lateral pressure of the surrounding earth, preventing a catastrophic collapse. Every step, every landing, every pillar was a load-bearing element in this subterranean labyrinth, carefully calculated through generations of empirical knowledge. Drainage was another silent triumph. During the torrential monsoon rains, the entire structure was designed to become a funnel, channeling runoff efficiently into the central reservoir while preventing erosion of the intricate stairways. The result was a space of remarkable climate control. As you descend, the air grows noticeably cooler and more humid, a natural refuge from the blistering heat above. This made it a social hub, a community center where people gathered not just for water, but for conversation, for ceremony, and for respite. To build such a thing today with machinery would be a significant but straightforward excavation and construction project. We could dig the hole with backhoes and line it with reinforced concrete. Yet that would miss the soul of the achievement entirely. The ancient stepwells represent a holistic engineering art form where utility, architecture, community, and spirituality were inseparable. The ornate carvings of deities, the symmetry that mirrors cosmic order, the very experience of the descent, all were part of the design. It was infrastructure as a spiritual and social experience, a place that acknowledged the sacredness of the resource it held. Replicating that would require more than technical specs. It would demand a culture that views a public utility not as a hidden pipe, but as a place worthy of profound beauty and communal reverence, a carved prayer to the life-giving power of water itself. These temples of stone and water are testaments to a deep reverence, but on the islands of Malta, that reverence was carved into the landscape on a scale that predates history itself. The megalithic temples of Malta, structures like, are not just ancient, they are foundational. They were raised over 1,000 years before the Great Pyramid of Giza, centuries before the first stones of Stonehenge were set in place. They stand as the oldest freestanding stone structures on Earth, built by a Neolithic people who left no written language, no grand cities, only these colossal, enigmatic monuments. Walking among the ruins, you are confronted by a profound contradiction. The society that built them is classified as simple, a farming culture with stone tools, no metal and no wheels. Yet their architectural ambition was anything but simple. They moved massive blocks of coralline limestone, some weighing over 50 tons, across the rocky terrain. They then engineered these behemoths into complex, apsidal designs, a series of connected, semicircular chambers that resemble the shape of a clover leaf. The construction technique is the classic post and lintel. where upright slabs support horizontal capstones, forming doorways and roofs. But here, the scale transforms the familiar into the miraculous. The lintels themselves are multi-ton slabs, precisely fitted atop towering uprights. This required an intuitive, advanced understanding of load bearing, of how to distribute the immense weight of stone across supports to create stable, enclosed spaces that have endured for well over 5,000 years. The mystery is not merely one of mechanics, but of motive and memory. How did a society without pulleys or draft animals orchestrate the movement of such stones? The likely answer is a symphony of manpower, using log rollers, ropes made from plant fibers, and earthen ramps. But envisioning the process is staggering, a project demanding the coordinated labor of the entire community, likely for generations, all directed by a powerful, shared belief. The stones themselves offer a clue. Many are pockmarked with spherical depressions, likely sockets for the wooden beams used as levers or fulcrums during positioning, a silent fossil of their ingenious, low-tech methodology. Yet an even deeper mystery shrouds these sites. After a millennium of extraordinary temple building, this culture abruptly stopped. The great complexes were deliberately closed, their altars and ceremonial spaces sealed. Then, the people themselves seem to vanish from the archaeological record. There is no evidence of invasion, no layer of destruction. It is as if the cultural imperative that drove them to such heights of cooperative engineering simply dissipated, leaving their silent stone circles to the wind. To attempt a replication today using only the tools we believe they had would be a project of almost unimaginable social endurance. It would require not just the physical labor, but the complete buy-in of a modern community, willing to devote years of their lives to a single, non-utilitarian goal driven by a faith or a vision we can no longer fully comprehend. The temples of Malta, therefore, are more than architectural wonders. They are a lesson in the power of collective belief to move literal mountains, and a haunting reminder that even the most stable, enduring societies can reach a peak, and then choose, for reasons lost to time, to simply walk away from their own greatest creations. But a mountain of pure copper presented a different kind of challenge, one of sustained, brute force applied with patient intelligence. On the remote, fog-shrouded isle in Lake Superior and the rugged peninsula, the earth holds a treasure not of gold, but of elemental metal. Here, over 6,000 years ago, indigenous peoples discovered veins of nearly pure copper, some weighing hundreds of pounds, lying just beneath the surface or exposed in cliffs. This was not ore that needed smelting. This was nature's gift, metal in its ready-to-use form, and they set about retrieving it with a determination that transformed the continent. Their tools were astonishingly simple, heavy stone hammers made from hard cobbles, and the clever application of fire. The technique, known as fire setting, was a slow, rhythmic dance with the rock. They would build a hot fire directly against the copper-bearing stone. Once the rock was superheated, they would douse it with cold water. The sudden thermal shock caused the stone to fracture and split, freeing the malleable copper metal within. Then, with those stone hammers, they would pound and pry the copper free. Imagine the scene, the smell of smoke and steam in a deep pit, the echoing ring of stone on stone, the gleam of a raw copper mass emerging from the shattered rock after days of effort. This was not a small-scale operation. Over centuries, perhaps, these ancient miners removed an estimated millions of pounds of copper. The landscape is still with their work, thousands of shallow pits and trenches, and piles of discarded stone hammers that number in the tens of thousands. The logistical challenge is staggering. Isle is a remote island, accessible only by boat across often treacherous waters. To sustain mining crews there, even seasonally, required advanced planning, reliable watercraft, and the ability to provision workers in a harsh, boreal environment. The copper itself then had to be transported back to the mainland and across vast distances. Archaeologists find artifacts made from this distinctive Great Lakes copper all across North America, from the Atlantic coast to the Rocky Mountains. It became a fundamental engine of trade, shaping regional economies and cultural exchange for thousands of years. Modern mining is a symphony of mechanized violence, with dynamite, diesel-powered excavators, and continent-spanning supply chains. To replicate the ancient feat means abandoning all of that. It means returning to that remote shoreline with nothing but stones, fire, and human muscle. The scale of their achievement is not measured in the purity of the metal, which was already pure, but in the monumental, collective effort it represents. This was not a rush for wealth, but a sustained, generational enterprise that organized labor, mastered a difficult environment, and produced a commodity so valuable it connected distant cultures. Each stone hammer, left in a pile where it was last used, is a silent testament to a different economic logic, one where value was measured not in coin, but in the enduring utility of a perfect tool and the far-reaching connections it forged. The simple act of raising water against gravity is one of humanity's oldest struggles, yet a solution from over 2,000 years ago still turns in our fields and factories. Attributed to the Greek polymath Archimedes in the 3rd century before the Common Era, the device that bears his name is in turning a brilliant observation into a tangible tool. It is, in essence, a large screw inside a hollow pipe. When one end is placed in a water source and the mechanism is turned, the rotating spiral lifts the water up the tube, delivering it to a higher level. Its operation is a direct application of fundamental principles, where the inclined plane of the screw thread and the mechanics of rotation work together to trap and elevate fluid with remarkable efficiency. The sheer elegance of this design is its greatest strength. It requires no complex valves or precise seals. It can be built from wood, from metal, or even from modern plastics. It is powered by a person turning a crank, by an animal walking in a circle, or by a modern electric motor, scaling seamlessly from a garden tool to an industrial machine. For ancient farmers, this was nothing short of transformative. It meant irrigation could reach fields that were slightly above a river or a canal, turning marginal land into productive soil. On ships, a larger version could efficiently pump out bilge water, keeping vessels seaworthy and saving countless lives from the hardship of foundering at sea. This was engineering that directly amplified human and animal effort, channeling it into one of civilization's most critical tasks. Today, you can still see Archimedes screws in action. They churn slowly in treatment plants, gently lifting solid-laden water without the need for filters that might clog. They turn in agricultural settings, moving water with a reliability and simplicity that modern pumps often complicate. We can manufacture them with computer-guided precision, but the core invention remains untouched. The true feat, however, was not in the crafting of the screw, but in the leap of thought that created it from first principles. Archimedes, or the ingenious minds of his era, looked at a problem as old as agriculture itself and saw a solution in a spiral. They understood that the path of least resistance for water could be guided upward, not with a desperate scooping action, but with a smooth, continuous motion. This device stands as a quiet monument to a specific kind of genius, one that does not seek the most powerful solution, but the most gracefully efficient one. It solved a persistent problem so perfectly that its design has never needed a fundamental revision, only new materials to build it from. In a world racing toward complexity, the enduring screw whispers a timeless lesson. Sometimes, the most advanced engineering is not about adding more parts, but about discovering the singular, elegant shape that makes the problem solve itself. The elegant simplicity of a spiral lifting water stands in stark contrast to the monumental ambition of a city built from the bones of a continent. Far to the south, in the heart of modern-day Zimbabwe, a kingdom of stone rose from a granite plateau, its silent walls telling a story of power, precision, and a profound connection to the earth. The great enclosure is the crowning achievement of this civilization, a vast elliptical wall that curves gracefully across the landscape, built entirely without mortar from precisely shaped blocks of a local stone called coral. To stand before it is to feel a sense of awe not just at its size, but at its presence. The walls soar up to 36 feet high and are an astonishing 16 feet thick at their base, a sheer curtain of fitted stone that has gravity and time for over half a millennium. This was not a defensive barrier in a conventional sense, but a statement of sovereignty and spiritual authority, a physical manifestation of a society at its zenith. The engineering here is in dry stone technique, pushed to a monumental scale. Each block of granite was carefully, then shaped by hand with stone hammers. The builders did not aim for perfect rectangles, but for interlocking, multifaceted forms that would grip one another through friction and balance alone. The walls themselves are not static lines. They are dynamic forms that curve and taper as they rise, their shapes subtly changing to follow the natural contours of the hill and to manage the immense structural load. This tapering is not merely aesthetic, it is a critical calculation in stone. By making the wall thinner at the top than at the base, the builders lowered its center of gravity, creating a stable, weighted structure that could withstand centuries of wind, rain, and thermal expansion without a single drop of binding cement. The precision of the fit is what truly stuns the modern observer. The stones are laid in even, consistent courses, their joints so tight that in many places, not even a blade of grass can find purchase. This required an army of highly skilled masons working in concert, a level of organization that speaks to a complex, hierarchical society with master builders who could translate grand architectural visions into flawless stonework. Replicating such a feat today with modern machinery would be a task of brute force. We could quarry the stone and stack it. But to replicate it, as the builders of Great Zimbabwe did, using only hand tools and an empirical, generational knowledge of local materials, presents a different challenge entirely. It requires surrendering our reliance on mortar and rebar, and instead developing an intuitive feel for the stone itself, learning to listen for the click of a perfect fit, to see the hidden geometry in a rough granite block that will lock it permanently into a soaring wall. This knowledge was not written down. It was passed from mason to apprentice through a lifetime of practice, a living craft that turned a rocky hill into a regal capital. The walls of Great Zimbabwe do more than enclose a space. They embody a philosophy of building that is in constant dialogue with the landscape, using its very substance to create a legacy meant to endure as long as the plateau itself. They stand as a powerful reminder that some of the world's greatest engineering traditions flourished far from the Mediterranean or the Andes, in the very heart of Africa, where master builders raised kingdoms from granite and left behind a silence that echoes with skill. The silent, enduring stones of Great Zimbabwe speak of a harmony with place, a principle that finds a startlingly beautiful echo not in the past, but in our present, high in the thin air of the Himalayas. Here, a modern engineer has looked at a crisis and seen an answer written in the ancient language of ice and gravity. In the high desert of Ladakh, climate change is not a distant theory, but a visceral reality. Traditional glaciers, the region's frozen reservoirs, are receding. Springs are drying up, and farmers face the heartbreaking prospect of watching their crops wither just as they need water most in the spring planting season. Confronting this, engineer did not propose a massive concrete dam or an energy-intensive desalination plant. Instead, he looked to the wisdom inherent in the landscape itself and created the ice stupa, a form of artificial glacier that is a masterpiece of elegant, low-tech engineering. The process is deceptively simple, yet its intelligence is profound. In the deep winter, when water still flows in streams but the air is bitterly cold, a pipe is laid from a stream high up the mountain down to the village below. The natural gravitational pressure builds in the pipe. Instead of letting it flow freely, the pipe is turned vertically, creating a fountain that sprays into the freezing air. The water droplets instantly freeze as they fall, accumulating not in a flat sheet, but in a conical, dome-shaped mound that resembles the traditional Buddhist stupas that dot the region, hence the name. This conical shape is the first stroke of genius. A flat ice sheet would be exposed to the high-altitude sun and melt rapidly in the spring. The ice stupa's shape, however, presents a much smaller surface area to the sun relative to its massive volume. It melts slowly, gradually, like a time-release capsule of fresh water. By the time the peak of the growing season arrives, the stupa is steadily feeding the fields exactly when it is needed most. This is not a new technology in the sense of invented materials or complex machinery. It is a brilliant application of ancient, observable principles, the same principles that guided builders of subterranean qanats and Inca terrace channels. It harnesses gravity to create pressure, uses the temperature differential between water and air as a tool, and designs with natural geometry to control the rate of a natural process. Modern engineering often solves water problems with immense concrete infrastructure and huge energy inputs for pumping and treatment. The ice stupa requires no electricity after its initial setup, uses only local materials, and leaves no permanent mark on the fragile landscape. Its most powerful component is not a polymer or a microchip, but an idea, a deep understanding of phase change and solar geometry. To call it simple is to misunderstand it entirely. Its simplicity is the point, the hallmark of the most sophisticated kind of problem-solving, one that works with nature's existing forces rather than attempting to overwhelm them. In this way, the ice stupa is a bridge. It is a contemporary feat that proves the ancient engineering mindset is not a relic, but a vital, living philosophy. It demonstrates that the highest form of technical brilliance might not always lie in increasing complexity, but in the clarity to see the elegant, sustainable solution that was there all along, waiting in the flow of a stream and the chill of the winter air. It asks us a quiet, urgent question for our own time, as we face global challenges of resource management. What other profound solutions are we overlooking? Because we are trained to think only in terms of power rather than harmony, the ice stupa's elegant simplicity proves that the most profound solutions often lie in working with nature, not against it. Yet the path to such mastery is paved with trials, and sometimes with dramatic failure. In the sun-blasted granite quarries of Aswan, Egypt, lies the most instructive monument never raised. The unfinished obelisk remains fused to the living bedrock, a 1,168-ton ghost of what might have been. This colossal shaft, which would have stood over 130 feet tall, is not a finished wonder, but a fossilized snapshot of the engineering process itself, captured at the moment it went terribly wrong. A deep, fatal crack appeared in the granite during the final stages of extraction, forcing the ancient builders to abandon their work. Yet this very failure grants us a gift no perfect monument ever could, a clear, untouched archaeological record of their methods. The surrounding trench, painstakingly carved around the obelisk's form, is a textbook in stone. We can see the precise channels hammered out by teams of workers using nothing but pounders made of dolerite, a stone even harder than the red granite. These spherical stone balls, found in their thousands at the site, were the primary tool. Workers would have stood in the trench, swinging these heavy pounders in a relentless rhythm, pulverizing the granite along a marked line to create a deepening groove. It was a process of pure attrition, of reducing solid rock to dust by repeated, focused blows. The scale of labor this represents is written in the quarry floor. To free this single, titanic needle, workers would have had to pulverize and remove an estimated 3,000 cubic feet of solid granite just to create the trench around it. This was not a matter of weeks, but of many months, perhaps even years, of coordinated, deafening toil under the desert sun. Seeing the sheer physicality of the attempt, the immense volume of stone that had to be vanquished just to begin the moving process, makes the successful extraction, transport, and erection of all the other obelisks scattered across Egypt seem almost supernatural. The unfinished obelisk does more than show us a technique. It humanizes the entire endeavor. It whispers that these feats were not performed by mythical beings or with lost superscience, but by people. It involved backbreaking risk, the ever-present potential for catastrophic error, and an expenditure of effort that borders on the incomprehensible. That crack in the granite is a moment of profound vulnerability, a reminder that for every soaring monument that succeeded, there were likely attempts that did not, stories of heartbreak and recalculation lost to time. This single, failed project, therefore, elevates all the others. It underscores that every perfect obelisk that now stands was a victory snatched from the jaws of similar disaster, a testament not to infallibility, but to resilience, problem-solving, and the sheer, stubborn will to try again. In its silent, fractured presence, we find a deeper awe, one rooted not in mystery, but in a newfound respect for the immense human cost and courage etched into every successful stone. From the pyramids to Polynesian canoes, we have journeyed across continents and uncovering 30 testaments to human ingenuity. These feats are not just relics, they are mirrors. They reflect a fundamental truth about our species, that engineering is not merely about the tools available, but about the creativity, observation, and sheer determination of the human mind. With simple stones, they achieved precision that humbles our machines. With earth and water, they built cities that managed entire ecosystems. With memory and starlight, they navigated an ocean. Each one stands as a quiet argument against a simple, linear narrative of progress. They show us that knowledge is not a ladder we climb steadily upward, but a landscape where peaks of brilliance can rise, be sustained for centuries, and then sometimes fade from memory, leaving behind only silent, stone questions. This cyclical nature of discovery and loss is perhaps one of history's most profound lessons. We are not inherently smarter than those who came before. We simply stand on different ground, with different tools and different blind spots. Their sustainable, resilient designs, from the dancing pagodas to the self-healing harbors, whisper that some of the most advanced solutions are those that embrace harmony over domination. They built for longevity, for a timescale that stretched beyond individual lives and even beyond empires. As we now face our own era of challenges, from a changing climate to the careful management of our planet's resources, the wisdom of these ancient masters feels startlingly urgent. Their greatest lesson may be a simple shift in perspective, to see the world not as a warehouse of materials to be extracted, but as a partner in a delicate, enduring dialogue. To build not for the next quarter, but for the next century. To solve problems not by overwhelming nature with force, but by understanding its rhythms so deeply that our creations become a seamless part of them. So we leave you with a final reflection. Which of these 30 feats resonated with you the most? Was it the cosmic computer of the woven resilience of the Inca bridge, or the silent, perfect seams of an Inca wall? Share your thoughts in the comments below and let the conversation continue. If you were captivated by these mysteries of the past, be sure to subscribe and join us as we continue to unravel the hidden, astonishing chapters of human history.